As we go into Chapter 7, we'll be dealing with exponents and radical functions. They give a little introduction to how much does health insurance cost, and they made a little bar graph, and this is something we will look at in, I believe, topic 7.1. Now, these are the sections we will be covering, and again, what are available in your textbook. We do 1, 2, 3, 4. We're going to skip section 5. We do section 6. We're going to skip section 7. Again, good stuff that are normally in a college algebra course, but again, they're trying to cut down on what we have to go over so it's not too long. And then we do complex numbers. Now, keep in mind we have the additional exercises posted in 2 versions, and I also do review tests. What we're doing here, of course, is looking over the textbook and giving you an overview of what's there and perhaps a little strategy. So, topic 7.1. Radical expressions, functions, and models. And we'll be going over all of this. Square root and square root functions. Now, the number c is a square root of a if c squared equals a. And you'll see some examples of it right now. So we say 9 has a negative 3 and a positive 3 as square roots, because if we square a negative 3, we get a 9. And if we square a regular 3, a positive 3, we get a 9. And that's true of 25 as well. Now, when we look at this next one, that is negative 4, and keep in mind we're sort of thinking of it as if it were in a parenthesis. A negative 4 does not have a real number square root because there is no real number c such that if we square c, it will equal a negative 4. And what do they mean? Well, if we're going to square a negative number, for instance, it will always be positive. That is negative times negative. So that's why they're saying you can't have a negative 4 be a square root of something. If you square a negative number, it's always going to be positive. Okay, now let's look at some examples. Some of these we can just do either mentally or just looking at it. Find the 2 square roots of 64. Well, the square root of 64 is 8, so it could be a negative 8 that's squared or a positive 8. Now, one of the definitions we have here, though, is worth mentioning, and that is the principal square root. When we think of the principal, which is a PAL square root, it's the one that is positive. Okay? Now, another thing too, the symbol, this is called the radical sign. And what is under the radical sign, you'll hear shortly or see shortly, is called the radicand. And any number that might appear here is called the index or the index number. Now, if there is no number appearing in the radical sign, there's an implied 2 being there. We just don't write it. Okay? So this is equal to this, and we don't write the 2. The radical sign, the radicand, index number. So as we look at these examples, and they're asking us, I guess, for the principal square root here. Here, this will be 5. Now the principal square root of the 64 is 8. Then we apply the negative sign. And then here we take the square root of 25, which is 5, 64, which is 8. This one's a little tricky because you have to be careful of where you put the decimal. So here this has 4, so our square root needs to have 2. That is, if we square it then, timesing it by, we end up with 4 decimal places. Okay. All right, here are just a number of different ways to describe it. But all these, since they are under, or part of it is under a radical sign, they are called radical expressions. Now, what is under the radical sign, as we mentioned before, is the radicand. And the radicand here is 5, here it's A, 3A, all of this, just the 8, just the X, I should say. The 8 is not under the radical sign. And we use our calculator to approximate. We would hit the square root sign, then we'd hit 5, then we'd hit enter, and then it gives you this. And again, it continues to go on. That's why it's called a irrational number. It just estimates it at this. But then they usually ask you to do it to 3 decimal places. And you would look at the 4th decimal place, and if that was 5 or above, you would add 1 to the 6. 4 or less, you just drop it. Okay, and then remember we had said if this were a perfect square underneath it, it's a rational number, but if it's not a perfect square, then it is an irrational number. We did that in Math 100 at Chapter 1. Now, what is the domain of these? Let's take a look at that for a moment. Now, under the radical sign, we just said that you can't have a negative value under the radical sign if it's an even root here, or the square root. So what we have to say over here is x is greater than or equal to 0 in order for it not to be a negative under the radical sign. So what would be the domain of this? Well, there's the domain. So in set builder notation, it would be x is such that x is, actually you just would write this, x is greater or equal to 0. That would be set builder notation. And in interval notation, and let's just do the graph of this. So it's going to start at 0. We're going to use a bracket, and then we're facing it out this way. And then interval notation of this would be, right from the graph, 0 with a bracket, and this would go off to positive infinity. And basically, that's what they have there. And by the way, this is the graph of this function. We did have throughout this course and 100 graphs that would represent various equations. All right, let's go on. Okay, example 3. For each function, find the indicated function value. Okay. Well, here they're asking us to do some substitution of what they are defining as our x here in our function. We just take the 1, put it where the x was. So this is 3 minus 2, which is the square root of 1, which equals 1. And then here in this function, where the z is, which they're evaluating as 3, we go 6 times 3 is 18, plus 4 is the negative square root of 22. That would be the actual answer. If we put it into our calculator to approximate, we get this. And if we round to 3 places, we would drop these because that is not 5 or higher. Okay. You will be doing some practice. Now, expressions in the form of the square root of a squared. Now, something I like to mention to students, as I mentioned a little bit already, there is a 2 there, and in a future section in chapter 7, we can convert this from radical form into what we call fractional exponential form. And again, we're jumping ahead here a little bit, but that's okay. That we take our base, or our radicand, which becomes the base, with its exponent, and then we take the radical index number here, which is 2, and that 2 is actually the denominator of that particular exponent. So in a sense, now we have a fractional exponent, 2 over 2, which is a 1, as you will see. So when we see a radical expression that has an exponent on the radicand, which is part of the radicand, and no number in the index spot, that 2 that's there is actually the denominator of that exponent. And again, it becomes a 1, which is, in this case, it's a 1, which is just what A is. So, if we have 5 squared, let's just do that here. The square root of 5 squared, there's a 2 there. I take away the radical sign, that becomes 5 2 over 2, which is 5 to the first, which is 5. Now, this one, of course, 0 squared is just 0. Now, Here we have a negative 5, but when we square a negative 5, it becomes a positive 25. So because of the parenthesis here and the squared, this is not equivalent to a negative 25 under the radical sign. This is a negative 5 squared, which in a sense, when we square a negative 5, we get a 25, which is a 5. Remember, it's not a negative 5. All right, let's go on. Well, we want to see whether these are identities, or in a sense are true statements. So here we said this was true. And this is also true. This is also true. This they're saying is not true. And this, this one we say in general could be true as well. And this is true. Now let's look at this number 6 here. If we convert that to its decimal, its fractional exponent form, it would be x to the 8th. Remember there was a 2 there, divided by 2, so this gives you x to the 4th. So that one's true. The only one that's not true is this one. So that was interactive discovery. Now let's look at some of the background of it. When we simplify anything that's like this, for any real number a, and once again I like the idea that we've introduced this, that there was a 2 there, so that when you take away the radical sign, this becomes a to the 2 over 2, which is a to the first, which is a. Remember, it could have been a negative 5 that we're squaring. So the use of the absolute value of this is really justified, because that would have included a negative value in there that came out as a plus. And you recall when we did this, absolute value of a equals 5. We said a could be a 5 or a could be a negative 5. That's from an earlier section we did. All right, let's go on. So we have done this already, and if we graph it, remember we get the typical absolute value shaped graph. So let's just go through what they have as they do their solutions. So here we have the absolute value of 36. I should say the radical value of 36 is t squared, is 6t, the quantity squared. Now they could have been this, or this. Now, I'm going to say up front that I'm not going to be super critical of if you're writing these answers out, whether you've put the absolute value there. Just so you know, it could have been an absolute value. And in some cases, that kind of protects you and gives you that negative value as well. Okay, letter B, that's straightforward. Now, letter C, notice this is a perfect square trinomial that we then put into its factored form with our 2, and then we take the square root of something, and it gives us that. And it's saying that that could have been negative, or it could have been positive. The absolute value protects that you cover yourself. Now, notice that when you have something like this, a to the 4th raised to the 2nd gives you a to the 8th. That a to the 4th is never negative, so you don't have to put it in absolute value. Why? Because by squaring any negative would have made it positive. So it does get a little deep. Now, but this could have been a negative, so thus t to the 6th, you would have to protect it by the absolute value. Now, Math Lab may be a little critical about this, but I'm not. Put your mind at rest here a little bit. Okay, here we're going to say that the expression being squared is non-negative. Therefore, absolute value notation is not necessary. So here's a good case where we can just do it with the 2 there. Remove the radical sign. This becomes y 2 over 2. That's just going to be y. Remove the radical sign. 10 over 2, a to the 5th. This is a perfect square trinomial. As you see, just removing the radical sign, 2 over 2 becomes this. And we're assuming that it's non-negative. Okay, cube roots now. We say 2 is the cube root of 8 because 2 cubed, which is 2 times 2 times 2, is 8. Now, negative 4 can be cubed because a negative times a negative gives you a positive, times a negative gives you a negative. So the general rule is, if you have an index number that is odd, that is 3, 5, 7, 9, and so forth, you are allowed to have a negative sign under the radical. And just to review, if the negative sign is even 2, 4, 6, 8, you are not allowed to have a negative sign under the radical. And there's the basic rule. Now the graph of it is very typical, cube root. Looks like that. Do you remember the one for y equals x cubed? recall, it was like that. So you see, when you're taking the cube root of something, it's sort of taking that same shape and then spreading it out more toward the x-axis. Okay? And let's take a look at the graphing of this down below here. Now the square root of x squared gives you the absolute value of x, which is this graph, and the cube root gives you x, which is, keep in mind it's like y equals x, would be this line. Okay, so something to think about here. So for 7, they're asking us to substitute this value for the y. So the cube root of 125, which is a perfect cube, is 5. And then here we're going to put in there a negative 24, which makes it a negative 27. And it's okay since it is an odd index number, which is a negative 3. So 3 times 3 times 3 is 27. A negative 3 times a negative 3 is a positive 9. Times a negative 3 is a negative 27. So that checks out. And when we go to simplify this, now remember, a way to look at that is, this is sort of like the third root. Well, I have that there already. This is like going to be a negative 2 cubed, which is a negative 8, y to the third, and that is raised to the, we then take our radical sign away, and then this becomes a 3 under this. That is what we're going to be doing in the next section. This then becomes a negative 2 because this is a 1 and y, and that's what they have here. So in a sense, it's a way to look at it, and I'm trying to give you a little insight to what's coming up. Okay. Now they do review this of odd and even n roots. Okay. So now let's just do some general examples here. And since they're all written out, let's just study them as we kind of look at them together. Now 32, believe it or not, is a perfect fifth. So that just becomes 2. Now because this is an odd number, a negative 32 is good as well. That's a negative 2. Now here it's the positive root, but because of the negative sign in front, whatever we get becomes negative. Now here we have a negative 2, where we then apply the negative, so this ends up being a positive 2. And here we have, using that little technique we talked about, 7 over 7 is 1, so that's just x. Again, we're going to get to that in the next section, as we will with this one too. The 9 is the denominator of this 9, and then you just get what's there. Okay, so again, whether you master this, is you'll work on the practice and then your quiz-mes. And here they're referring to odd roots, even roots. Again, if it's an even root, you cannot have something with a negative sign under the radicand. But here, it could have been something that was raised to the fourth power, so you would put absolute value. Okay, let's look at these two. Now, 16 is a perfect fourth, so that's 2. Now, because of the negative sign, that will become a negative 2. This one, because it's an even index number, and a negative under the radical is not a real number. Now, 81 is a perfect fourth power, so that becomes 3. X, and then 4 divided by 4 is just x to the first. And you could list it this way or this way. And again, I will not be critical on that. MATLAB may be. And then here we have the 6. Take away the radical sign, put it under this 6, just makes it a 1. And there is that in a radical sign. Because you're ensuring that if this were a negative, it's protected. Again, I won't be critical of that. And here's the little summary. Okay, determine the domain of the function given by this. Well, because this is an even root, can this value under the radical sign ever be negative? And the answer is no. So the technique for solving this, the strategy, would be to say that this radicand is greater or equal to 0. And that's what they're doing. And then you solve it, and you get x is less than or equal to this. Now, again, we did mention this earlier. How could you have something less than? Isn't that going to make this number smaller and eventually negative? And the answer is yes. But notice this value over here is negative times something. So as this gets to be a negative, that would make this a positive. So we had done one very similar to this earlier in our lesson. In fact, let me give you a simple example. The square root of 5 minus x. Okay? Now, this then we equal to, or we say 5 minus x is greater or equal to 0. So we transpose the x, and over here it's an x. So our answer is that x is less than or equal to 5. So for instance, is 6 good here? If we put a 6 there, 5 minus 6 makes this a negative 1. If x is 7, it makes this a negative 2. And as we get numbers that are larger here than 5, this is negative. That's why negative numbers are okay. if x is a negative 4, we go negative times a negative 4 makes it a positive 4. So that's what they're illustrating. And then they're putting it in set builder notation and interval notation. So even though common sense you'd say, well, how come they're negative numbers? It's because this value here is negative. So whatever negative number here by a negative makes it a positive. Hopefully that helps. And I see this is a long lesson, and they are using some graphing that we're going to skip. And they're asking us to use the calculator for this, so we'll skip that too. And to use a calculator for this. Okay, that'll wrap up topic 1.